Try it again. All right, you're both pushing. And who has a bigger acceleration? Jerry. The smaller mass person has the bigger acceleration. All right, come back together. Do it. All right, this time, Jerry, just hold your hands up. Just Alan's going to push. Should we see a difference? So even with just Alan pushing, right, Jerry's got the bigger acceleration. All right, this time, just Jerry push. Alan, just put your hands up and let him push you. What did he say? Just push off of him. Are you holding on over there?
Just me push.
Just you push.
Same bumper boards here.
All right. He still has a bigger acceleration, right? Okay, you can get off now.
What?
You can get off. All right. So our smaller mass object has a bigger acceleration, right? Yes, you guys did a very good job. And it doesn't matter who's applying the force, right? Remember in our spring scales, it didn't matter who was pulling, they still have the same force, right? So if he's pushing, it doesn't matter. Jerry, both of them are going to have the same force. Okay? No matter who's pushing, whether they're both pushing or just one person is pushing, they both feel the same force. And since one of them has a smaller mass than the other, the person with the smaller mass is going to have a bigger acceleration, right? Okay. All right, what are our elephant gun stats?
Okay, in the 19th century, there were 4-bore rifles with 130 gram slug, 430 meters per second.
That would hurt.
Yeah.
That would hurt.
It's 130 gram slug.
Yeah, I don't know how that translates to caliber.
It was related to shotgun gauges, 10.86 and 4, and even 2-bore. So 2-bore slug, well, an 8-gauge slug is, I don't even know, that's huge. Bigger than your phone. An 80 solid one. So, I don't even know. I mean, about a golf ball size.
Wow. Wow. I'm guessing if you're laying down, you're going to have a better shot of firing that without.
They shot elephants in the head, and they had to use those size bullets to puncture the bone because it's a very thick skull.
Oh.
And when they were using the 12-gauge rifles of the day that they used for birdshot, bullets were bouncing off of the eyelids.
Pissing them off, really.
Yeah.
You're just making them mad at that point, yeah. Okay. All right. So for the collision for the two people on the skateboard, it's the same deal, right? The one with the larger mass is going to experience a smaller acceleration. What's that? He's the truck, you're the car, exactly. Except instead of hitting, you guys are kind of exploding outwards or something. Yeah, I don't know what we would call that. Yes, right? But larger mass, slower acceleration, bigger mass. I just said the same thing. Smaller mass, bigger acceleration. Yes. Oh. Okay. All right. So we want to look at the acceleration a little bit more. I know for some people, acceleration is probably very intuitive, but for me, it never was. As a student, I had to work my way through it because it was not intuitive. Meters per second, that's intuitive to me. I can kind of visualize running or doing motion at meters per second. But meters per second squared for me was never something that just clicked for me. So I'm going to walk through it, and if it makes sense to you already, you can feel free to tune me out. That's okay. I won't be offended. All right, so the way I think of acceleration is if we have 10 meters per second squared, like in that first guy, really what's happening is we're getting 10 meters per second every second. Okay? So if we start off at 20 meters per second, okay, after 1 second, we're going to gain another 10 meters per second. Okay, so 1 second later, we're going to be up to 30 meters per second. Right? If we wait another second, we're going to gain another 10 meters per second. So after one more second, we're going to be up to 40 meters per second. Okay, so an acceleration of 10 meters per second squared, this guy is I always think of it like this, meters per second. For whatever reason, that works better for me. But it's the same thing as 10 meters per second squared, which, like I said, for me in my head is not intuitive, and maybe it is for all of you guys, so more power to you. For me, it's not. So 20 meters per second squared would mean every second you're gaining 20 meters per second. So if your speed started off at 30, 1 second later you're going to be at 50. You're going to gain that 20 meters per second every second. Okay? So in this case, our acceleration is positive, 10 meters per second squared. So our net force, what sign will it have, positive or negative? Positive, right? If I made our velocity positive, positive 20, that means our motion is this way. Our net force is this way, so we expect to see it speed up, right? Which is what it's doing. It's starting at 20, now it's at 30, then it's at 40. So it's speeding up. Okay? So let's look at the same thing, 10 meters per second squared. Right, is 10 meters per second. Right, that's our A. But let's say we start off with minus 40 meters per second. So our motion is in this direction. Okay. So 1 second later, what's our speed going to be? Minus 30. Yeah, so we've dropped down to minus 30 meters per second. And after another second, we're going to be down to minus 20 meters per second. So we're still moving to the left, but we're slowing down. Right here we were moving at 40 meters per second was our speed. 30, 20, we're dropping down. So we're slowing down. So our acceleration is positive, which means our net force is that way. But since our motion is negative, our motion is this way. So it's like you moving this way and somebody pushing against you. You're going to be slowing down, which is what our numbers show us. Right? We're losing speed. We're slowing down. Eventually we're going to hit 0, right? And once we hit 0, what happens? If we keep the same acceleration, yeah, it's going to start pushing us back in the other direction, and we're going to start gaining speed, right? So let's just look at a negative acceleration and make sure it works out for us. So let's say it's negative 10 meters per second squared. I could have kept that. All right, so if we're moving at 20 meters per second, our acceleration is negative. What are we going to be 1 second later? 10. Right, we're going to start losing speed. Okay, so if our acceleration is negative, our net force is negative. So our net force is this way. If we have a positive speed, we're moving that way, but our net force is working against us. So we expect to see us slowing down, which is what's happening. We've gone from 20 to 10, right? And if we go back over here, we make this guy negative. That's terrible. There we go. All right. Did that backwards. Minus 40 meters per second. All right, so if we have a minus 40 meters per second as our velocity, our acceleration is negative. That means we're moving this way. Our velocity is negative. Our acceleration and our force are pointing this way, so we expect to speed up, right? It's working with us. So 1 second later, we're going to gain negative 10, so we're going to be at what? Negative 50, right? We're going to be at negative 50 meters per second. And in the next second, we will be negative 60 meters per second. Okay. So we are picking up speed, but we're moving leftward. Because our force is pushing us leftward, we're already moving that way, we're going to gain speed. Okay, we're going to start going faster. Okay. Actually, let's leave that. Okay. So up and down, it's going to work. Are we okay with this? Everybody okay with side to side? All right, let's look at up and down. Up and down, our acceleration, we all heard the number, right? 9.8 meters per second squared. We're going to round it to 10 so I can add it in my head. All right, it's actually negative 10. Okay, we're going to, convention, our convention is down is negative, so our acceleration is going to be negative 10. So if we have an object that is falling, so he's falling, our tennis ball or whatever is falling, let's say it starts with a minus 20 meters per second. Right? 1 second later, it's a little bit further down, but 1 second later, what's its speed going to be? Negative 30, right? It's going to be picking up speed as it falls. So it's going to go to minus 30 meters per second. Okay? If it's falling, its motion is down. The net force of gravity is also down. So our net force is pushing us or pulling us in the direction we're already going, so we're going to speed up. So we're going to pick up 10 meters per second every second as we head down. Well, pick up negative 10 meters per second every second. So an object that's falling is going to speed up. Okay? Let's go back over here and let's do an object going up. All right. So let's say we've thrown our object into the air, so its motion is upward. Okay, so it might be moving at 20 meters per second. Right? 1 second later, how fast is it going to be going? 10. It's going to lose a negative 10, right? Or it's going to change by negative 10. So 1 second later, it's going to have a speed of 10 meters per second. Right? And this is because if your motion is this way, and your acceleration and your force are this way, right, you're going to slow down. So our object is going to slow down as it goes up. All right. So what we want to ask then is at the very peak, right at the top, what's our acceleration there?
0.
And what's our speed at the top? 0. What's our acceleration at the top? Yeah, this is this is a catcher. It catches a lot of people. It's a tricky question for many people.
Top.
At the very top.
It's not doing anything.
It's come to a momentary stop there. What's your acceleration?
No acceleration.
Okay. All right. Do we agree with that? He's saying there's no acceleration at the very top. Where did I hear that from? That's okay. Why do you disagree? Tell us. Oh, I agree. All right, so ask yourself this. If the acceleration is 0, even for a split second, is it ever going to move again? It would hover. If your acceleration is 0 at the top, it's not going anywhere. It's not going to ever gain speed.
The acceleration of gravity.
All the way through. All the way up, it's negative, the acceleration of gravity. At the top, it's the acceleration of gravity. And all the way down, it's the acceleration of gravity. And that's a real big common answer, is that at the top, we visualize it as stopping.
Or if you throw it.
Even if you throw it.
It's different.
Okay, all right. If you throw it, once it leaves your hand,
It's a decrease.
but once it leaves your hand, what's its acceleration?
Yeah, you're not doing anything.
Same thing, right? While it's in your hand, the acceleration is different, right? But once it leaves your hand, it's just acceleration of gravity, because the force of your hand is done once it leaves.
What about a baseball pitch when it's trying sideways?
All right, when you're going sideways, right, there's Y motion and X motion. And in your Y motion, you have acceleration. So on the way up, the Y motion is slowing down, and on the way down, the Y motion is speeding up. But your X motion, the sideways motion, the whole way through is the same, because gravity doesn't work sideways, right?
Okay.
So our X acceleration in that case would be 0. But your Y acceleration, even at the top, is negative 9.8. Because if your acceleration became suddenly 0 up there, you're not going to move, right? It would hover there. It wouldn't move. So all the way up at the top and all the way back down, the acceleration is negative 10 or negative 9.8. Okay? And it's negative unless you define down as positive, which I hate doing. But sometimes they do that. It confuses me, yeah, because I'm so used to doing it the other way. I don't like when they do that. And it confuses my students. The signs are already tough enough. That really does confuse them, trips them up. All right.
Is there like a visual that you could actually do for fun that you can demonstrate that?
So a visual to demonstrate the acceleration.
Yeah, how it's,
Well, we could throw an object up,
okay.
right? And on the way up, it's going to be slowing down, and then it kind of stops up here. but on the way down it's speeding up. But other than that, do you guys, any physics guys or any teachers have an idea? A way to visually demonstrate this? The acceleration being -10 all the way up and -10 down and -10 at the top. Any other ideas for explaining it either? I mean, how do you explain it to your students? How do you guys explain it?
Gravity's always active.
Gravity's always
You always
active.
have to emphasize that it is positive velocity, but not now it is negative velocity.
It's negative velocity going down, right? Negative or positive going up. Yeah.
You're spinning more faster in the negative direction.
So, yeah, I think gravity is always working is probably a good way to put it. It's not like gravity stops working on you when you come to a rest.
Yeah, when you're at the
Yeah.
very top, it's still.
Yeah, picture it as you, right? If you're up there and you come to a rest, you don't think, whew, that's over. Right? It's just starting. The bad part's about to come. Yeah. It's sort of like if you think sideways motion, right? If something is slowing down and the force is continuing, it's going to turn it around and push it back, right? And momentarily it stops, but it doesn't stay stopped.
Like jumping on a trampoline.
Mm-hmm. Yeah, and when you're jumping on the trampoline, you know when you hit the top because you get that, ooh, feels kind of funny. Yeah.
I
Yeah.
just need a visual picture.
Yeah, yeah. Okay, so from this, let's say we are moving at 5 meters per second. 1 second later, we don't know what our speed is. 1 second later, we don't know what our speed is. But out here, we know we're moving at 20 meters per second. What's our acceleration in that case? 5 meters per second, right? So in this case, our acceleration is plus 5 meters per second every second, which is 5 meters per second squared. All right. Because we can kind of work through that in our head, but let's do one with numbers a little bit goofier. Let's say we start at 1 meter per second. 1 second later, we don't know what we're doing. How far am I going to go with this? Let's do another second, and let's end up at 2.5, 5.5, right? Yes, 5.5. All right, yeah, this one's not as easy to do. All right, how are we going to figure out, because we don't know our in-between, how are we going to figure out what our acceleration is here? So let me,
Definition of acceleration.
yes, that's what we're getting to.
Oh.
That's what we're trying to find. So we're starting off at 1 meter per second. 1 second, 1 second. We're getting there. What did I have, 5? Yeah. 5 meters per second.
Said 5.5.
Okay, where's
5.5.
5.5?
Yeah, you said you put.
Oh, did I have 5.5? Oh, sorry, 5.5. I thought you were trying to tell me the answer was 5.5.
No.
Thank you. All right, 5.5. Yeah, that's better. I like that. All right, so how are we going to find our acceleration here?
Change in velocity.
Mm-hmm. If you think about what you're really doing here when you're doing it in your head, right? You're taking 20 minus 5 and dividing it by 3, right? That's really what you're doing in your head. You just probably don't think through it. You're doing 20 minus 5, right, divided by 3. So you've got 15 divided by 3. And that gives you 5, okay? But this is easy math, so we just push through it, okay? Over here, if we wanted to do it, we could do 5.5 minus 1 divided by 3, because that's how much time it took, and what's that going to give us? 1.5 meters per second every second. Okay? Right? So we're doing 1.5 meters per second every second. So we could actually fill this in. What's our speed here?
2.5.
2.5. What's our speed here? 4, right? Those are our in-between steps, okay? All right. Go back to this guy because he's easier at math for us. You could do 20 minus 5 divided by 3. We know the in-between spots. This is 10 meters per second. This is 15 meters per second. We could also use any other 2 points here. This is all the small chalk on this end. Big chalk. So we could do 20 minus 5 divided by 3, and that gave us 15 divided by 3, which gave us the 5 meters per second squared. What if we use the 15 and the 5 instead? So then we had 15 minus 5. How many seconds would that be? 2, right? So 15 minus 5 is 10. 10 divided by 2 is 5. We're going to get the exact same answer. We're going to get 5 meters per second squared, right? What if we use the 15 and the 10? Right? We would have 15 minus 10, and what's our time in between those guys? 1, right? And we are going to get, shocking, 5, right? So it doesn't matter which 2 points we pick, we're going to get the same thing. We just need to know how much time happens between those 2 points. Okay? And let's do one with negative numbers just to say we did. All right. Is everybody okay with the positive? Are we okay? Positive. Let's make these guys negative. Okay. So what's our acceleration going to be? Negative 5 meters per second squared. But the math is still going to give it to us. So if we do the negative 20 minus a negative 5, and it's 3 seconds, right? That's negative 20 plus 5. So now we're up to negative 15. That's right. Negative 20. These two minuses give us a plus. So we've got a negative 20 and a plus 5. So we're going to get a negative 15 over 3, and we're going to get a negative 5 meters per second squared. Okay, so it's still going to work. Okay, so a general expression for this is up here. We can find our acceleration if we take a v final or a v2. Sometimes the textbooks don't even put a subscript on the final v. It's just plain old v. And we subtract a v initial. So one that happens later in time minus one that happened earlier in time. And we divide it by the time. How much time is in between those two? Which is exactly what we did over here. Right? That's my v final. That's my v initial. That's my time. Okay. So are we comfortable with this guy? Right? We just, like I said, we just did it. This is v final, that's v initial, that's our time. And it gives us our acceleration. Okay. All right, so F equals ma, so we can put that in for a. Right? Then we're going to multiply the m in, so we're going to end up with this guy. mv final minus mv initial over t. It's just another way of writing force. Okay. All right, mv is very important, shows up all the time. That's our momentum. Okay. It looks very what? Oh. Oh. Yeah. How are the crime scene stuff? Is it neat that she's doing? It looks really fun. Okay. All right. So we've got momentum is mv, so we can write our force this way. Okay. So we can put in the p's. So the mvf is p final, that's our final momentum. The mv initial is our initial momentum. Okay. And let's look at our units, just to make sure. So we have F equals ma. We look at units for that. Mass is in kilograms. Right? Acceleration is in meters per second squared. That thing is a newton. We call those newtons. Right? If we look at it in terms of momentum, right, it would be the units of mv. So m is that, v is meters per second, minus kilograms meters per second, over the time, which is going to be in seconds. Okay? So our units on top are kilograms, meters per second, and our units on the bottom are seconds, right? Which is kilograms, meters per second squared, which is the same as that. Okay? So F equals ma, and F equals your change in momentum over time, the exact same units, because they're giving you force, they're going to give you newtons. Depends on what they give you in a problem, right? If you know an acceleration, you're going to go F equals ma. If you know a V final and a V initial and that kind of stuff, you're going to work with this one. Okay, but they're both for force. Okay. This one is actually, I find, very helpful. If you want to make the force small, what can you do to the right-hand side of that equal sign? What parameter, let's say time. We want a small force. What kind of time do we want? A big time, right? And if we want a small force, what kind of change in momentum do we want? Small change in momentum. So ask yourself this. If you're in a car accident and your initial momentum is based upon you going 50 miles an hour, and your final momentum is based on you going 49 miles per hour, that's a pretty small change in momentum, right? That's a good collision, right? Because you're only going from 50 to 49. But what if you start off at 50 miles per hour and you go to 0 miles per hour? That's going to make the top of that fraction much bigger, right? And that's a bad collision. Bad things happen to you, right? Time is what we were going to do our water balloons with, which we may not end up doing. But we've got a couple videos on ways to increase time in collisions, because your car is designed to make the time of a collision longer. Your seatbelt does two things. One of them is prevents you from going through the windshield. The other is your seatbelt has just a tiny little bit of give to it, because what you're trying to do in a collision is make the time that it takes you to stop very big. Because if the time it takes you to stop is very big, your force is smaller. So your seatbelt has just a little bit of give. So in addition to stopping you from going through the windshield, it's made to give a little bit. Same thing with your airbag. Your airbag is not made to stop you instantaneously. Right? If it was, they could pop lead out at you, right? I mean, and bring you to a dead stop, and that would really hurt, right? Yeah. One of the things that your airbag does is make the time bigger, because if this is bigger, that's smaller, right? So your car actually has what's called a crumple zone on it. Okay? We're going to watch a little video. This is a British video, so kind of, it's British humor, you know. Just a heads up on that one. They talk about our car crumple zone. Okay.
Hello and welcome to today's lecture from Brick University.
They're Legos.
Hi, I'm Nick.
And I'm Jane.
Today we're going to look at momentum and how we can use this to understand why we need crumple zones in our cars. Let's start off by looking at some theory on the whiteboard. Let's remind ourselves that momentum is equal to mass times velocity. If our car weighs 1,000 kilograms and it is travelling at 25 meters per second, what is its momentum?
Wait, what is
That's right,
it?
you've got it.
25,000, right?
kilograms meters per second. What happens when a car hits a wall? Because the car's velocity becomes zero, its momentum must change to zero during the collision. We can use the change of momentum formula to allow us to find the force that acts on the driver during the collision. Rearranging the formula, we get force.
They're kind of doing it backwards from what we did it. This is what, right, we just talked about. This is the one where we're talking we want to increase our time to get a smaller force. Yeah, they do. They're goofy. They drive on the left-hand
Equal
side.
to change of momentum divided by the time over which the collision acts. Now we can use this formula to see how we can reduce the force on the driver. Because the change of momentum will be the same for any specific collision, if we increase the time, it will make the force smaller. Now we can put this theory into practice by looking at crumple zones in a real collision. Let's go over to our brave stunt driver, Ollie. Ollie, are you ready to go?
I think so.
So this is with his crumple zone. And this is without his crumple zone.
Oh dear, I hope Ollie was okay after that second crash. Now let's go back to the whiteboard to see if we can work out the forces involved in those two collisions. So the car had a mass of 500 kilograms and a velocity of 10 meters per second. In the first collision, when the car had a crumple zone, the car and the wall were in contact for 1 second. So if we put those numbers into the formula, we can see we get a force of 5,000 newtons. Now let's look at the second collision. In this one, the car had no crumple zone. So the car had the same change of momentum, because it was still 500 kilograms, going at a velocity of 10 meters per second, but the contact time between the wall and the car was only 0.2 seconds. So if we put these numbers into the formula, this time we get a force that's much greater of 25,000 newtons, which is why poor old Ollie ended up being thrown out of his seat. You'll be pleased to know that Ollie has made a full recovery and will be ready to do some more experiments for us next week. That's all for this edition. So it's goodbye from me.
And goodbye from me.
All right, so the crumple zone is designed specifically to increase the time that it takes your car, right, to stop. And they don't just have the crumple zone, they have a safety cage kind of around the passenger compartment, right? So the next video is actually shows us an old car, the Chevy Bel Air from 1959, back when they made tanks, right? And the Chevy Malibu, so a 2009 Chevy Malibu. And they're going at about 40 miles per hour. They're going to do an offset head-on collision. And the question is now, which one would you rather be in before that collision? Which car is going to be safer in that collision? The old tank versus the Chevy Malibu.
The new.
Right, so let's watch. After the accident, they both look pretty horrible, but when we see the video camera from inside the car, you can kind of see which one you'd rather be in.
That's the Insurance Institute for Highway Safety's front crash of a 2009 Chevrolet Malibu and a 1959 Chevrolet Bel Air. In slow motion, you can see the differences in how the new and classic cars perform in this version
Isn't that awful?
of the traditional
Yeah, he's
frontal
dead.
offset test. The Institute conducted this test to commemorate its 50th anniversary.
Now, the
And
Malibu has a
how
big
much
crumple
improvement has
zone.
been made in passenger protection since the non-profit organization
But like I said, when we get to
opened
the
its doors.
inside,
The two cars collide in an explosion of
look at the
metal, glass,
windshield
and
on this
plastic.
guy. His
Where
windshield,
the
like,
Malibu crumple zone absorbs much of the crash forces ahead of the windshield. The Bel Air structure allows the lighter car to compress the passenger compartment. The impact is made worse for the Bel Air driver by the lack of airbags, head restraint,
Yeah.
and even a seatbelt.
He died
As a
instantly.
result, injuries to the
We
neck,
like to tell
chest, and
ourselves.
both legs would be likely. Consequently, the Bel Air receives a poor rating across the board.
Yeah.
On the other hand, the modern Malibu provides good protection, with the dummy movement being well controlled. Measures indicate a low risk to most body regions, though a foot injury would be possible.
Yeah.
Beyond the safety gear, advancements in vehicle engineering give the Malibu a clear advantage in this matchup. While classic cars are often considered to be rock solid, this 59 demonstrates how much better today's cars are. And the IHS has played a key role in driving these advancements. The past 50 years, the Institute has made a real impact. The roads today are safer for it.
you know, I never got that, yeah. Yeah, because I tended to think, of the old cars, those are tanks, nothing's gonna, but no, they aren't designed to maximize your time. So it's a very bad collision in one of those guys. And you see it now with the cars when they're in an accident, the front ends are all mushed up, but the passenger compartment's usually pretty good. All right. When a tanker hits them, or when a train hits them, yeah. There's only so much they can take. Light posts are another good example. This is also British, so there's deal with the Brit thing. They're driving, the airbag comes off on the wrong side. You're looking at the car and you see it poof up on what we would call the passenger side of the car. But another good time explanation, or not explanation, but example of why you want to increase that time in your collision. Oops, let me go back. Get my mouse down here.
High up on the list of potential killers, lampposts.
Lampposts.
Lampposts are everywhere. Over 6 million of the things on British roads, just a foot or two from the tarmac. Some are protected by crash barriers, but most aren't. And if you hit them, it can be very nasty indeed. So what damage can they cause?
Well, allow me to demonstrate. We've put up this typical British lamppost. It's 12 metres high, it's made out of very solid galvanised steel tube, and it would cost you about £750, including installation and bulb. We're going to hit it at 45 miles an hour using this well-preserved Rover 820 SI. Now, this would be far too dangerous a test, even for a stunt driver to perform. So we fitted the car with remote control. And it'll actually be driven from a chase car following behind at a safe distance. That is, after I've got out, obviously.
Obviously. I don't know what a Rover is. Is that like a Land Rover? What's a
Let's go.
Rover car?
The lamppost stopped the car from a speed of 45 miles an hour in less than a metre. People inside would suffer massive deceleration forces, compounded as the car is forced up and thrown violently round to the right. Rooted in concrete, the lamppost hardly absorbs any energy from the crash, only bending a few inches through the soil. The driver and any passengers would probably have suffered serious neck, back and chest injuries, or much worse. The human body can't cope.
Oh, sorry. I'm sorry. The human body can't cope. Sorry. Hold on. We'll go back. I was going to say where I lived in Washington, Pennsylvania, if you hit the lamppost, you paid for it. Yeah, you had to pay for it because people were running away from it because they didn't want to pay for them. Let's go back. I think we're about there. To make you pay for the what? Somebody was telling me that in Texas they had to pay for the cow if you hit it. Oh. And I'm like, really? Keep the cows off the road. Okay, it's freaking out on me here. Come on. Play.
And high up on the list of potential killers,
Norway, Sweden, the Netherlands.
worse. The human body can't
There we go.
cope with being thrown around so aggressively.
But it needn't be like this in Finland, Norway, Sweden, the Netherlands and parts of the United States. They've been using safer lampposts for years. They come in various types. This one's made out of light stainless steel, but they're all designed to do the same thing. Slow you down more gently so the damage to the car is less, but more importantly the people inside the car are safer.
This one's called the Larson Safety Post, and this is the man who sells it in the UK, Guy Wadsworth. He's prepared to
Very
put his
British
life
name.
on the line to show us how safe it is. He's going to drive straight into his lamppost at 45 miles an hour in another Rover 800.
So, Guy, 45 miles an hour into a lamppost, are you sure you want to do this?
Yes, I don't see why not. It's one of those Victor Kian moments. You know, I believe in the product. I know what's going to happen. I'm quite confident.
What is going to happen?
When I hit it, it's going to go very noisy, and then the car will effectively run the lamppost over, having bent it in half, so it'll use the whole length of the pole to slow the car down.
Are you taking any extra safety precautions at all?
No, I'm replicating what's going to happen to the public. You know, I'm wearing my tweed, and, you know, as you would if you were driving on Monday. The only difference is...
His tweed. He's in his tweed.
I know I'm going to have an accident, like most people. And that's really just in case the glass gets broken somewhere, but, you know, it's eminently safe.
Yeah. So he puts a helmet on, theoretically to keep the glass off, but then he keeps the visor on the helmet up, so I'm not sure.
Guy may appear confident, but this test has never been attempted before using a real driver. In fact, the test so extraordinary that a delegation of top road safety experts has flown over from Sweden to observe it. Guy really is putting his life on the line.
Guy's crazy. Yeah.
Oh, big.
It's like it smacks you.
Yeah.
Bad driver. Yeah.
Oh, there goes that camera.
They check him out here and ask him if he's okay, but he's fine. So I think it's a liability thing. Is your neck okay?
Okay, keep still, you can do it, keep still, keep looking, keep looking, keep looking. Down your neck, pain in your neck? Absolutely not. Head in your back? Absolutely not. With your fingers? Yeah. Okay, take your hand off the side.
Wadsworth is fine, and his tweed is okay.
Wow.
Yeah, fine. The Glasgow was a bit of a shock, but I was going rather fast and I thought it was.
In fact, with the adrenaline flowing, Guy actually hit the lamppost at 50 miles an hour.
Wow.
But he still walked away completely uninjured. On impact, the post collapses in a controlled way, running under the car, helping to bring it to a survivable stop. The top of the lamppost coils round, dissipating vital energy. It slams into the roof, but it's light enough not to cause severe damage. The deceleration forces involved are a tiny fraction of those in the previous crash. And the car, though heavily battle-scarred, was still drivable. Various types of safer lampposts are now starting to make an appearance in Britain. But as they're more expensive than ordinary posts, they'll be used mainly on major roads and at accident black spots. Similar technology is also improving the safety of road signs and traffic lights. It'll be a long time before we catch up with countries like Sweden and Norway, but I hope we do. I'd much prefer to hit this than this.
Bam. Yeah, that one hurts. Right, so the idea is to increase the time on the bottom of your force fraction. Because if you increase the time, then you're decreasing your force. Right, and we're gonna stop there because that's actually a good stopping spot. And I'll see some of you.